Welcome to this QuickTake video on the UltraFast Design Methodology for the Vivado Design Suite. This QuickTake focuses on the major topic of board and device planning. This QuickTake is only an overview and not meant to be a comprehensive guide, so be sure to take advantage of the extensive UltraFast materials on board and device planning. Before we get started, note the following background materials that may improve your understanding of this QuickTake. UltraFast Design Methodology for the Vivado Design Suite. Introduction and Overview. This QuickTake covers some basic principles of the UltraFast methodology and how it ties into the design process, including board and device planning. I/O Planning Overview. This QuickTake introduces the I/O planning process and how to use the I/O planning feature in Vivado. Also helpful is the Vivado Design Suite User Guide, I/O and Clock Planning. UG 899 covers assigning device package pin locations for optimal connections to other PCB components and clocking selections to maximize performance. And as always, visit the Xilinx website for the latest user guides, training materials, and QuickTake videos. Within the UltraFast Design Methodology User Guide, UG 949, Board and Device Planning is a major chapter, currently Chapter 2. Board and Device Planning is also covered by an UltraFast Design Methodology checklist to ensure you have not overlooked some key aspects of planning. Recalling the basic UltraFast philosophy, more effort is spent during the early stages so that less effort is spent later in the cycle trying to fix difficult problems. And notice board and device planning occurs at the very beginning of the design cycle and has perhaps the greatest impact on the success of your designs. In this QuickTake, we'll explore these major board and device planning subtopics. Board layout recommendations, emphasizing the importance of balancing board layout needs with placement of related device resources. I/O and clock planning. Clocking selections may dictate specific I/O requirements, and I/O assignments impact the flow of data through the device. And power considerations. It is essential to ensure you are reasonably within not only your power budget, but also within your thermal management capabilities. Let's begin with some basic recommendations for layout of the printed circuit board or PCB, or just board layout for short. UltraFast covers many recommendations, including ensuring the device is properly oriented on the board, getting familiar with the device pinout, and knowing upfront which pins have dedicated or dual-purpose functions, which are power supplies and ground pins, what pins are used for configuration, they are often dual purpose, and transceiver pins, which are dedicated pins. Consider the locations of the components that interface to the device, and use pins on the edge to minimize trace lengths and avoid vias. Consult the PCB Design User Guide for your device family as a reference for other important board tasks, including device configuration. Determine what method will be used to configure devices and which pins will be used, I/O and clock resources, and designing with memory interface IPs. And the PCB Design User Guide also covers how to generate critical data for the system designers, such as the actual device I/O pin assignments, simultaneous switching noise or SSN analysis results, and IBIS simulation models for signal integrity analysis. Now taking a look at a conceptual high-level project schedule, board layout is typically completed very early in the cycle to start the manufacturing process and finish fabrication. Once system assembly is done and design closure has been achieved, the system can move on to the bring up and debug phase. After board layout is complete, I/O assignments become locked down for the remainder of the design closure process. That means that you may miss the opportunity to evaluate whether design closure is being impacted by suboptimal I/O pin assignments. Suboptimal placement of the I/O package pins may cause inefficient data flow through the device, which can reduce performance and extend the design closure process with many more place and route iterations, as it is too expensive and impactful to the schedule to even consider small changes to the board layout. So when an opportunity arises, consider shifting some burden to board layout to accommodate device-friendly I/O assignments. As UltraFast asserts, extra effort early in the design cycle will ultimately reduce many costly late-cycle iterations. One example of suboptimal I/O assignments is when related I/O are placed too far apart. To illustrate, let's use a hypothetical device based on recent architectures, with I/O columns in the center, surrounded by logic regions and gigabit transceivers which also have dedicated I/O along the edge. Say there is a high-speed I/O interface block A, could be a memory interface IP for example, located as such, and it communicates with the transceiver block A, which is placed nearby in the same row. But it also communicates with GTB and high-speed block C, which are located relatively far due to their I/O assignments. Traversing longer distances will require pipeline registers to maintain the clock speed. If the blocks cannot be located closer to block A, then the design must be able to tolerate some latency to be able to run at a minimum clock speed. But there can be problems with I/O interfaces located too closely. Here's a similar example with high-speed block A and GTA placed closely in the same row. A similar pair of high-speed I/O block B and related GT are placed in the next I/O column in the same row. Related high-speed logic will tend to be drawn toward the I/O in the I/O bank and remain in the same row to share the same global clocking resources. Depending on the sizes of the blocks and connectivity and placement of other modules in the design, there may be some competition for resources in the same row, which could lead to congestion. So you may want to consider other locations if possible, or consider staggering the I/O placement. I/O planning can uncover problems even more effectively when including the key pieces of the design, such as the high-speed I/O interfaces, or even mock-ups of key IP. Use the I/O planning flow in Vivado to explore the implications of I/O pin assignments. The I/O planning layout presents side-by-side views of the package, showing the physical pin locations for board layout, and the device view, which concurrently displays the related device resources so that you can instantly evaluate the impact of I/O pin locations on the related device resource locations. I/O planning is typically an interactive process using Vivado Projects. With an I/O planning project, you can begin with only the I/O ports, or you can begin entirely from scratch and create the I/O ports, and define and validate I/O properties such as I/O standards and I/O bank compatibility, and perform other important tasks like simultaneous switching noise analysis. An RTL project adds I/O related logic including clock generation circuitry, and note that a full design is not necessary. A skeleton design is sufficient for finding problems with I/O assignments and running clocking design rule checks. Use IP Integrator to quickly craft a skeleton design containing the key IP blocks such as memory interface and gigabit transceiver IPs, and clocking resources like MMCMs and PLLs. The extra effort of putting together a skeleton design is worth the reward of uncovering potential issues during I/O planning. Additional planning is needed when targeting a 3D IC device, also known as Stacked Silicon Interconnect or SSI. An SSI device consists of superlogic regions or SLRs that are connected using interposers, also known as super long lines. The interposers interconnect the SLRs, transferring configuration, clock, and signals in between them. One SLR acts as the master SLR and controls configuration of the overall device. At a high level, you can think of SSI as being multiple dies interconnected on a substrate. We won't go into further detail here, but the Xilinx website has a wealth of background on SSI technology. Here are some tips for planning SSI devices. SLRs can suffer congestion and performance issues when overutilized. Try to avoid I/O assignments that draw too much logic in any one particular SLR. It's better to have balanced utilization. There are a finite number of SLL connections between SLRs, and they incur non-trivial delays when crossing between SLRs. So also, try to avoid I/O assignments that require many SLR crossings and require long-distance connections between SLRs. If an I/O interface cannot fit into a single I/O bank, try to at least keep it within the same SLR. Crossing SLRs at high speeds will require pipeline registers to maintain clock speed. Finally, note the number of available I/O in each SLR, as the total varies between different packages. Now let's move on to power planning. An important part of power planning is to determine what voltage supplies are necessary to power the device. Besides the core supply VCC int, there are additional supplies needed for block RAMs, I/O, transceivers, and potentially many other supplies depending on the target device, For example, if using the processing system of the Xilinx UltraScale Plus MPSoC. With so many different supplies powering the device, it becomes important to follow the correct power-up sequence. And note that an external voltage reference is required in some cases, such as when using the XADC or system monitor or a differential I/O. Run the Xilinx Power Estimator XPE to get a first-order estimate of the power supply currents and the thermal margin. XPE is a free spreadsheet-based tool downloadable from the Xilinx website. To get the most accurate estimate, be sure to enter reasonable settings for the device resources entered on the individual sheets, choose maximum process for worst-case estimates, and operating environment considering ambient temperature, airflow, and board thickness. Thermal margin is increasingly more important as devices grow in size and capability and dissipate more power. XPE can help you determine if thermal management will become critical and advanced solutions are required, such as the use of heat pipes or vapor chambers. XPE estimates the current per supply rail, which helps choose voltage regulators and voltage supply ICs. Here are some useful references for designing device power needs into the system. The Packaging and Pinouts Product Specification User Guide with detailed information on the packages, power supplies, pin functions, and gigabit transceivers. This is UG575 for UltraScale and UltraScale Plus, and UG1075 for Xilinx UltraScale Plus MPSoCs, and the Xilinx Power Estimator User Guide UG440 describes all aspects of power estimation and how to get the most accurate results. To summarize, we've covered the UltraFast topic of board and device planning, with key elements being board layout recommendations, emphasizing the importance of balancing board layout needs with placement of related device resources, I/O and clock planning, choosing optimal locations for I/O, and power considerations to ensure you stay within power budgets and thermal management capabilities. Board and device planning is covered in Chapter 2 of UG949 and is supplemented by an UltraFast Design Methodology checklist in DocNav, and also keep in mind the extensive materials on I/O planning flows in Vivado. Visit the Xilinx website for the other UltraFast Design Methodology QuickTakes, as well as other helpful QuickTakes user guides and training materials. And finally, be sure to follow Xilinx on social media for important updates. Thank you for watching.